obvious, right? You take just any mode symmetric matrix, real symmetric matrix, or a Seyfert joint matrix. Look at the powers and look at, say, the first diagonal entry. That forms a moment sequence, which is not very obvious. And first diagonal is not important. You can take the second diagonal entry. Then also it's a moment sequence. You always get a moment sequence. Okay, that's what this is saying. Okay, so they come from the pure states. Okay, instead of diagonal entries, you can take the trace. That they also form a moment sequence. Okay, so it's something quite amazing that one matrix here will contain so many different random variables. Depending upon your state rho, it contains all those random variables. Okay, just compactly hidden there. Okay. So let me go further. I wanted to continue a little more on this kind of general theory. Then we'll go to specific things like moments. Okay. So the next thing. So we have these expectations of the moments. So then same way I can take variance. If I take A as trace of x, okay, this is the expectation of x. Okay. So what is the variance of x? Variance. So this is, by definition, is the expectation of x minus a square. Right? So which is trace rho x minus a whole square. Now you can expand it. X square minus 2ax plus a square. So a is just this number, trace rho x. So this is trace rho x square minus 2a trace rho x plus a square. Trace of rho is 1. But trace rho x is a, so this is trace rho x square minus a square. So in other words, this is the usual expectation of x square. Okay. Minus expectation of x. Your typical formula for the variance, the same thing holds. There is no difference. So this is the variance. Same way you can define covariance. If I have two of them.
Linearity is still there, so that takes care of it.
Yeah, so the linearity is there. So the covariance of x comma y, okay, again I will keep it. So this is trace rho xy, okay, the same thing. Trace rho xy minus trace rho x into trace rho y. Right? This is the expectation. Okay. So this is by definition the covariance. Okay. Trace rho xy minus, you can also write it as trace rho x minus the expectation into y minus the expectation. Write that with that just by linear. But one thing to note here, though x and y are Seyfert joint, x times y may not be Seyfert joint. So this may not be a real number. Okay? So in general, this is a complex number. Okay? This covariance. So if x and y commute, then it becomes real. Then xy is Seyfert joint. So then it becomes real. Okay? It belongs to R if xy equal to y. Okay. So now I want to do some interesting things using this idea. have two observables or two random variables. The variance, the product of the variance is bounded below by this. You cannot reduce the variance below this. Okay, so there is a lower bound for the variances. Whatever you do, the product of the variance is greater than or equal to this. So this depends upon this one. What is x?
It's commutator.
It's the commutator. Okay. So for commuting random variables, it is 0. Okay, so that will give you 0. So the lower bound becomes 0. But it is interesting for the non-commuting thing that you get a lower bound like this. So this is Heisenberg's uncertainty principle.
There's a proper physical meaning also.
Yeah.
There's a proper physical meaning also.
Very much. So for proper physical meaning, you have to go to unbounded operators. So you take the operators which are position and momentum, and it's saying that whatever way you try to measure it, if you try to make your measurement of position accurate,
Precise
the other things will escape. You are not able to make the momentum measurement precise. And conversely, so there is a lower bound time. That is Heisenberg's uncertainty principle. Okay. So this is a sort of baby version of that. The real version would need unbounded operators, and the actual version where the physics people used it.
Why did you say baby version? Because you took pure state or?
We have taken bounded operators.
Pure state and bound operators.
Yeah, and yeah.
This particular theorem can you prove for unbound operators also?
Yeah, there are versions. And the main thing they wanted was for the position and momentum, where the commutator becomes essentially a scalar, which is a very strange thing, because then you know that whatever you take, you just get that constant out, right? So you get a fixed number then. Here it is not like that. It depends upon u, and you don't know if you vary u, how small it can become. So maybe it can become 0 for some use, right?
Yeah.
Right.
The commutator, depending on the commutator.
It depends upon the commutator and this vector u. When you are varying u, it depends upon the commutator. Okay. Whereas in the unbounded case, when the x commutator y is just a scalar, which is not possible with bounded operators. Okay, that's a theorem that you cannot have the commutator as a scalar. Okay. Okay. Let us do this fast. This is okay. I have just taken these two numbers, the expectations, u times xu, v as u times yu. So then this one u I times xy u. This is same as u I times x minus a y minus b u. See, when you have a commutator x comma y, even if I add a constant here, it will not change because the identity commutes with everything. Okay. So that's why I can, for this, I am subtracting this scalar, this set scalar. Whatever scalar if you add with x or y, the commutator will not change. Okay. So this is I times. So it's a commutator x minus a times y. My inner products are linear in the second variable, so I take that I outside. So this becomes x minus a u, y minus b u, minus the other way around.
Optimize or something?
No, it is just straightforward Cauchy-Schwarz inequality.
Just
Just Cauchy-Schwarz. So this is some x plus iy, this is some x minus iy. So if you, because this is the conjugate of this. So what you get is just the I times the imaginary part. Okay? So because this is some number z, this is z bar, right? So you get the I times the imaginary part. So the I into I, well, 2 times that, right? I'm just saying if z is x plus iy, other one is minus x minus iy. So if you subtract, I will get 2 times I times the imaginary part.
Then I.
So this, that I and this I gives you, so I square which is minus 1, so you get minus 2 times the imaginary part of this. Now we can take Cauchy Schwarz and you will see that. So it will give you 4 times norm squares of this. So bring the 4 to this side, you will get 1 by 4, and this is just the variance. X minus AU norm square is just x minus AU, x minus AU, which you take, this is x minus A whole square, so which is the variance of x, because A is the expectation. So this is 4 times variance of x and variance of y. So that is what we wanted to show. Okay. So it just shows Cauchy Schwarz, nothing else. Okay. Okay. So that is the reason I put it is actually because it is connected with the Heisenberg concept.
Is it possible to go for general states?
Well, I think it is possible, but it would be, I don't know what exactly. This one.
Is there a version of Markov inequality here? It's a different question.
Yeah. Markov-Chebyshev inequality, one can have some certain versions of it. Okay.
That would be for a Markov process.
No, it is something else. It is a simple inequality
Very
for
easy.
distributions. Just connecting the moment and the distribution.
Tail
Another nice thing I want to do, here is another theorem. So it's called Bell's inequality. So let x, y, z be independent variables. Taking values in the interval -1 to 1. -1 to 1. So what do we want to say? So then one minus expectation of xy is greater than or equal to again, it's a very elementary inequality. Okay, nothing complicated. Just a 2-line proof.
Doesn't have to mean zero or anything.
Huh?
Mean zero.
Nothing. Okay. By the way, all the things I am doing are from this book of K.R. Parthasarathi. any three numbers. So then obviously I have 1 is greater than or equal to y, okay, because they are in minus 1 to 1, and also 1 plus x is positive. Okay, so this gives you 1 plus x greater than or equal to y into 1 plus x. Right, I just multiply that. So this gives me, I bring this xy to this side, and so I get 1 minus xy is greater than or equal to, gives you y minus x. But x and x, y, z, just any three numbers, right? So 1 minus xy is greater than or equal to y minus x. So it is also greater than or equal to x minus y. So by symmetry, if 1 minus xy is greater than or equal to x minus y modulus. Okay? Which is greater than or equal to, I can multiply by mod z. Okay, because mod z is greater than or equal to 1. So I get this. So just remember these two things. So I have this. Zx minus z. So this is true for any three real numbers x, y, z between minus 1 and plus 1. Okay. That implies it's also true for these random variables. Evaluate the random variable at any omega, the inequality is true. Okay, random variables are functions and taking values in the interval minus 1 to 1. Okay, so these all these random variables x, y, z, they are functions from some omega taking values in minus 1 to 1. Okay, so if this is true for real numbers, it's also true for this. That means all this means is that at every omega here you have this inequality. So if that is the case, then I can take the expectation and the same inequality holds. Okay. But this is 1 minus expectation of xy, and this is greater than or equal to expectation of modulus of this is greater than or equal to, let me write it once. Expectation of this modulus. That is always true. The expectation of the f x modulus of x is greater than or equal to expectation of x modulus. So this is true. So that's all. So it completes the proof.
I will give it to my students.
Yeah. Very, very nice, simple thing. So you would ask me why such a elementary inequality, there is such a name, and why is it important? Okay, this has led to a lot of discussions in quantum theory. This Bell's inequality. Okay, so the reason is that I can get three quantum random variables, that is the observables x, y, z, taking values in minus 1 to 1, okay, which violate this inequality, okay, for which this inequality is not true. Okay. So, see, one of the things we are bothered about, like we are modeling things, random things using this Hilbert space theory operators and so on. Maybe there is some other omega, some other sample space, some other classical setup where these x, y, z, etc. are functions of that. Okay, why should I take this quantum thing? Maybe there is some other space in the background of which these are functions, and we are actually doing that. So these are called hidden variable theory. Okay, the idea that maybe there is some other setup, okay, some bigger sample space, omega, bigger things of which these x, y, z, whenever we talk about these observables, they are real functions of that. Okay? So it is basically comes from classical theory. Okay, the hidden variable theory they call. There are many attempts to do that, and this was one of the things which says that that is not possible. Okay, because if they are classical